This is also, these 3 weeks that are coming up in the material are my favorite 3 weeks of the stuff that goes on in MATLAB and the tools that we're going to be covering. And this is why. So let me go back and just lay some context here. You want to predict motion in the roller coaster. So if you've got a track and you've got a cart at the top here, we know in our heart of hearts that we should be able to predict what happens when we let the cart go. This is what people do all the time. And there's obvious analogies to this, which are, taking something at the Earth here and launching a satellite and landing it on a comet. That's the same kind of thing. It's gravity and acceleration from a motor. Just one sort of in our living room and the other one's across many billions of miles of space. But it's the same thing. We're going to start with both of those with fundamental physics, grade 10 physics. And what we're going to do is go from that grade 10 physics into MATLAB and be able to predict what's going to happen next. From the technical side, there's going to be some kind of mass times acceleration thing, right? At the end of the day, sum of the forces equals ma, which means that we've got mx double prime running around. So this is going to be a differential equation if we include the whole thing here. Differential equation, because guess what? We have two derivatives running around of x. We've got the acceleration of our position. And our forces are going to depend on where we are as well. So these forces are going to depend on x. What we're going to want is the solution. So the idea is, as always, the differential equation is the rules for what's happening. I believe that F equals ma because I believe in Newton. Okay, second law is true. All right, then what does that let us predict? Well, at the end of the day, in math terms, we would have x of t equals. When you went through all the differential equation solving in your differential equation course, this is what you get. X of t equals at the end of the day. Now that, I think, totally misses the punch of all this, which is that this is a simulation or a prediction. You can think either way of what's going to happen. You don't launch spaceships from here to land on comets without simulating what's going to happen before you press the go button for real. You do it a whole bunch of times in simulation, and then you see, will this work in theory and in practice? What are the error bounds? That's what solving a differential equation is. It's simulation, it's prediction. And MATLAB's going to do the heavy lifting for us with this simulation prediction. So think of it that way. It'll make the output that we're going to look at, which is not going to be as obviously a simulation prediction as we'd like. That's what it is. If you think of it that way, it'll make a lot more sense when you're trying to work with both the inputs and the outputs. We're going to start off with something relatively straightforward. This is the heating and cooling law, which pretty much everyone saw in first year and then would have seen again in second year. Another one of Newton's laws, I might add. Newton's heating and cooling law, which says that the rate of temperature change is going to be equal to, or is proportional to, that's electrical, is proportional to the temperature difference. We saw this written small scale when we looked at the cells of our heat model. But this is it. If there's a big temperature difference, if I take something really, really, really hot and take it out of the oven, it's going to cool down faster than something really, really sort of medium temperature that I take out of the oven and put on the counter. The temperature rate of change is going to depend on how much difference there is, how quickly it's radiating heat to the environment, which is governed by the temperature difference. If you had to solve this kind of differential equation, what technique would you use? Anybody care to volunteer what they think the technique would be? Starts with S? Separable, exactly. Separate and integrate. It's actually linear too. It is first order linear, so you could use integrating factors as well. So you actually have a choice. So in this case here, we're back to the idea of, hey, I could get an analytic answer to this. And what we'd get here, y is our unknown variable. So our solution, the dry mathematical phrasing of that is that my solution, y of t, is equal to some constant e to the minus kt plus t exterior. Again, that robs this of all its impact. Okay, if I take something hot out of the oven and I want to know how long do I have to wait until it's cool enough so I can actually eat it without burning my mouth, well, that law doesn't tell me. That differential equation doesn't tell me. But my solution, which is a prediction or a simulation of what happens once I take things out of the oven, does let me tell or answer that kind of question. Because what we have here is a graph, a simulation of the temperature, which is y, over time. And I can simulate that it's going to take X number of minutes to get to some particular temperature, and that in the long run it's going to head down to some constant temperature. Oh wait, the environmental temperature, that's where we're going to end up in the long run. And that's great. So we can say, yeah, I can eat it once it's this temperature here. That's going to take 5 minutes. All right, that's what the solution or simulation tells you. That's much more informative, even though it's governed by the basic rule at the top, which is the how does heat work, period. This is how does heat work in our particular scenario. Now again, because we're going to be using numerical methods, we like to have an example like this where we know what the right answer is. This, I can predict what the temperature is over time using calculus, separation of variables, and so on. We're going to compare that with what we're going to have to do in MATLAB to solve the same equation and see what we can compare and contrast there. Just a reminder of what you would have to do to get these analytic, which is the by hand solutions here. You'd have to recognize it as separable. If you were one of the people who did not raise your hands and go, that's separable or linear, then you would stare at that all day and there's nothing you could do, right? If you don't recognize what technique solves this equation, you're out of luck. So that's a problem. You have to properly and accurately execute whatever the solution technique is, i.e. don't make a mistake when you're integrating. You have to include your plus c at the appropriate moment, then you have to solve for plus c, blah, blah, blah. And at the end of the day, again, you get this a e to the minus kt plus t exterior. So if you can do all those steps, that's fantastic. If you hit a barrier or hit a glitch along the way, it'd be nice to be able to check your answer with some other technique that wasn't just repeating your own work. Also, there might be some things where there is no solution technique for it. We'll see some examples like the roller coaster simulation where you can't solve it up front. There's things that are changing too dynamically, so we may not be able to get a solution. So we're going to need something else. What do we recognize? In principle, again, think of this track model. I have faith that if I know where this cart is at the beginning, and I know that sum of forces equals ma, that should be all we need to predict, to simulate the motion of the cart. We know that those are the rules. We know where we're starting. That somehow should be enough for us. In the analytics side, we have to bring in a whole bunch of math things that are not about the physics. They're about how am I going to manipulate those equations. But in principle, we shouldn't need to do that. So where does the problem come in? Well, it comes in from that integration step, from that finding the technique that's appropriate. What we can do instead is get an approximate solution without having to integrate. That is going to be fantastic. This is one of the things I like. We're going to simulate the behavior without actually having to do any integration differentiation at all. It's going to be awesome. So everything you learned in your differential equation class, it's great. You don't need it here. We're going to do it all from scratch again, but we're going to get MATLAB to do the heavy lifting for us. Hopefully that excites some of you at least. You're not going to go back and do characteristic equations and Laplace transforms. None of that here.